So the next speaker is Muzi from RIKEN-iTHEMS, and she is going to talk about cancellation of loop corrections to solve power spectrum of inflation. So please.
Thank you for the introduction. I'll talk about this, and this work is in collaboration with these collaborators, and the talk is based on 2 recent papers. I will start from introducing inflation, and then introduce loop corrections to cosmological perturbation and show the cancellation, and then briefly mention its relation to symmetry, and then conclude. Let me start from the introduction. So, as Derek mentioned, in the very early universe, the temperature was very high, and the universe was full of a soup of particles. Photons frequently scattered off electrons, and when the temperature dropped, electrons got caught by nuclei and atoms formed, and photons decoupled and free stream to us, and we observe them as cosmic microwave background. The temperature fluctuation of the CMB is very small, and we can ask why the pattern is so homogeneous and why there are fluctuations. The inflation period before the thermal history can actually provide an answer to it, and let me explain. But let me first explain why the homogeneity of CMB was a problem, and explain the expansion of the universe. So as a 2D analog of the expansion of the universe, you can think stretching a sheet or blowing up a balloon. So any 2 points getting away from each other because of the expansion. And we can define 2 kind of distances. The first is the comoving distance. So it's about how many cells between the 2 points, and this doesn't change because only the length of the cell changes, so you can see this A getting large. Another distance is the physical distance, and it's the comoving distance times the length A, and this gets stretched by the universe expansion. I also want to introduce the Hubble parameter. So it is the velocity of 2 points getting away from each other due to the universe expansion over the physical distance between them. And you can see the comoving distance cancelled, and the Hubble parameter only depends on the property of the scale factor A at that time. So the farther apart, the faster the separation grows. And when the separation of 2 points is sufficiently large, the universe expansion carrying them away from each other can be faster than the speed of light. And this leads to a characteristic length scale called Hubble horizon. So this C here is the local speed of light, and we use the C equals to 1 unit. When 2 points are separated farther than the Hubble horizon, we say they are out of Hubble horizon, and roughly speaking, they cannot communicate at that moment. For example, the equilibrium cannot be reached. So this Hubble horizon is in the sense of physical distance, and we can also have the comoving Hubble horizon, which is the Hubble horizon over the scale factor A. Now, from the beginning of the thermal history to close to today, the Hubble horizon and the comoving Hubble horizon both becomes larger. So more and more cells get into the Hubble horizon. Now, so at the time of photon decoupling, the CMB formation, the comoving Hubble horizon at that time is much smaller than today, around 10 to the power of -2. This is to say, so at the time of the CMB formation, around 10 to the power of 4 patches were out of contact. And then we can ask why we observe them as a homogeneous pattern. So in other words, so around 10,000 persons have the same haircut in a room just by coincidence. And this is strange, and we want to have an explanation to it. And so inflation can provide an answer to this puzzle during inflation, so it's before the beginning of thermal history. The Hubble horizon is almost a constant, and as time passes by, less cells are in the horizon. So these cells had once been in Hubble horizon during inflation, and this is not so strange. We observe them as a homogeneous pattern. And because because the Hubble constant is almost a constant now, so solving this equation, the scale factor grows exponentially, and we had accelerated expansion during inflation. And let me emphasize that the co-moving Hubble horizon first drops and then grows. And it drops till the end of inflation and then grows. Now, how to have inflation? The simplest model is single field slow roll inflation. So it's a slowly rolling scalar field, like it slowly rolls down on its potential. And the potential energy density of the field supports the inflationary spacetime. From the Einstein equation, we can write down the Hubble constant is expressed by this potential, and because it's slowly rolling down, so the potential is almost a constant, and we had a almost constant Hubble parameter during inflation. Now we answered the question of homogeneity problem and how about fluctuations. And inflation can also seize the fluctuation. So instead of a homogeneous background, we can consider perturbation around it. And so the perturbation of the scalar field sources the perturbation of space-time. But the story does not end here. The separation of background and perturbation can actually be changed by choosing another coordinate, or we say fixing another gauge. One way of doing this is after changing the coordinate, instead of using t prime, we keep the original coordinate label. So it's like when you derive the Lie derivative. Specifically, we can choose delta phi equals 0 gauge. And the physical perturbation does not disappear just because we choose delta phi equals 0. It is also encoded in the scalar fluctuation of the space-time metric. For example, by properly fixing the gauge, including the delta phi equals 0, it can appear as the fluctuation of the scale factor A. And from in the rest of the talk, I will treat this theta. Now the quantum fluctuations got stretched during inflation. This quantum fluctuation of scalar perturbation is mainly described by two-point correlator. You can think of as a quantum analog of covariance. And here xy is in the sense of co-moving coordinate. And after Fourier transformation, we can have the two-point correlator in the Fourier space. And because of momentum conservation, this only depends on one momentum. And we call this P the power spectrum. In this context, it is usually calculated at leading order by solving classical equation of motion. And so there are a lot of Fourier mode K, and when K is small, it means large spatial distance. And they get out of horizon early during inflation. And for large K, it means small spatial scale, and they exit on horizon later during inflation. And out of horizon, for the case of slow roll single field inflation, the power spectrum is conserved outside horizon. So when we want to calculate the power spectrum at the end of inflation, we just need to calculate them along the horizon exiting epoch. And for the single field slow roll inflation, it is almost the power spectrum is almost K independent. And then later, when they re-enter the horizon, they set the initial condition of CMB and also the structure formation as Derek just talked about. And the initial condition is random amplitude of theta for each K mode. And the probability distribution is near Gaussian, and the power spectrum specifies it. Now, as I mentioned, for the single field slow roll inflation, the power spectrum is almost k-independent. And for small k, so large scale, it is relevant to observation of CMB and large-scale structure. But the small scale is less constrained. So people can, for example, change the inflation background and have some enhanced mechanism later in inflation and enhance the small-scale perturbation. Now, because the fluctuation gets enhanced for small scale, when they re-enter the horizon, they can lead to the generation of primordial black holes, induced gravitational waves, and so on. Because for the modes way out of horizon, they are conserved. The enhancement mechanism cannot affect the modes which is way out of horizon. For example, the k goes to zero limit. This has already been established at the leading order calculation by solving the classical equation of motion. However, there is a recent claim which gathered a lot of attention in our community, and they claim that through higher order quantum corrections, the enhanced small scale has scale invariant corrections to large scale, including the superhorizon limit k goes to zero limit. So Yokoyama was my supervisor, but if this is true, then if the higher order corrections is too large, then the perturbative predictions might be threatened. For example, the correction is even larger than the tree level, then the established prediction method may not work. And this gathered a lot of attention, and a lot of discussion is following it. And in our result, we showed explicit cancellation at the soft limit k goes to zero limit at one loop level, and we also provide an explanation from symmetry. Okay, so let me introduce the loop corrections to cosmological perturbation. Let's consider a time model of zeta like this. So this prime is the time derivative, but it's the conformal time, which is defined by this. And inflation ends at tau equals 0. This has a dilatation symmetry, so when you rescale the spatial coordinate and change theta at the same time, this action remains the same. We consider this dilatation symmetry because single field inflation after fixing delta phi equals 0 gauge, zeta also has this symmetry. So the action of zeta in the case of single field inflation is like this, and F and CS is specified, and there are other terms with dilatation symmetry. The dilatation symmetry is a residual gauge symmetry after fixing the delta phi equals 0 gauge. And among these terms, we focus on local terms because they are related to the enhancement mechanism under debate. And we showed the result for both the toy model and the single field inflation. And let me emphasize that our result does not depend on the specific form of F and CS. We only assumed that the starting stage is slower inflation. So now we want to calculate the power spectrum and loop corrections to it. It is an expectation value of this operator at the end of inflation. So we use Stringer-Kaldich formalism in formalism to calculate it. We start from the Bunch-Davis vacuum and have time evolution forward and insert the this operator at the end of inflation, and then evolve back in time and go back to the Bunch-Davis vacuum. So when we do path integral, we need to integrate over this contour, this banded contour. And for simplicity, people usually split this contour into two parts, the plus branch and the minus branch. And so this tau integral can be rewritten like this. This minus branch has an extra minus sign because it's backward in time. And the action is rewritten as S zeta plus minus S zeta minus, where zeta plus lives on the plus branch and minus zeta minus lives on the minus branch. And sometimes for the simplicity of calculation, people can further change variables to the so-called Keldysh basis. It's a linear combination of zeta plus and zeta minus. And now the goal is to calculate zeta r at the expectation value of zeta r at the end of inflation. Now changing the variable to the Keldysh basis, we can rewrite as zeta plus minus S zeta minus as a functional of zeta r and zeta a. Now we expand the action, and there are terms with two zetas and their cubic terms, quadratic terms, and so on. Because zeta is a small quantity, so it has been considered that the main contribution comes from these quadratic terms. And we can calculate the free green functions, which are time-ordered two-point correlators, from this only from this quadratic part. And there are free green functions for GRR, GRA, and AA. And we use these kind of notions to express it. So GRA is proportional to a step function of time, which means that it is only non-zero when zeta a is earlier than zeta r. And GAA is just zero. So because of this kind of properties, sometimes it's easy to do the loop calculation in Keldysh basis. And the leading contribution to the power spectrum is the GRR in the Fourier space at the end of inflation. But we also want to know the loop corrections. And this needs contribution from this cubic and quadratic terms and so on. So we write down the diagrams, and the external line connects to these two-point correlators. And so if you don't know how to do the loop calculation, it's just, for example, you have one diagram and you write down the product of all the free green functions and do the integral at each vertex. And the vertex is provided by the terms in the action. And we can also transform this to the Fourier space, and then the integration is over momentum for each loop and over time for each vertex. Okay, now for the one-point green function, because zeta is just a fluctuation, the expectation value is zero, equals zero is imposed. And this is okay for the free part for the quadratic terms in the action, but the loop corrections are not zero. For example, at one loop level, we can have this kind of diagram. And to cancel it, we need to add another term to the action, so it's called a counter term with a proper coefficient c, which depends on time. And then we cancel the loop contribution and maintain this condition. This is called dipole renormalization. Okay, now let's recall that our goal is to calculate one loop corrections to the power spectrum at the k goes to 0 soft limit due to the enhancement mechanism. So the loop part, first we have this k cubic contribution from this definition of power spectrum. And then for the loops, we can classify them into three groups with different kind of external lines. So external lines with GR, and one GRA and GR, and two GRAs. The diagrams with two GR, they just vanishes because of the property of the RA basis. It just vanishes non-perturbatively, and we don't need to worry about it. And for the case of GRA, so we can show that in the case we are considering, the external line GRA does not have k singularity. So when we take k goes to 0 limit, it has a k cubic suppression, and this part just goes to 0 and gets suppressed. And we only need to consider this diagram, this group of diagram. So let's recall that we added a counter term, but the counter term also needs to have the dilatation symmetry, so we cannot just add one zeta. We need to add an exponential 3 zeta combination. Now so instead of have one zeta in the action for the tadpole renormalization, we have a tower of terms because we want to maintain the dilatation symmetry. And there is also a counter term containing the zeta A, zeta R, with its coefficient determined by the tadpole renormalization. And okay, I will skip all the calculation details. And we have shown that in the setup of the toy model and the single field inflation, the relevant diagrams and that counter term determined by tadpole renormalization vanishes at the soft limit k goes to 0 limit. And for your reference, so we also calculated the enhanced scalar perturbation of a spectator field, which is minimally coupled to gravity, and its contribution to the tensor fluctuation. And this also vanishes at the soft limit. Okay, now finally I will briefly talk about its relation to symmetry. So let's first recall that only this diagram, this group of diagrams contribute, and this vanishes, and this does not contribute. Now, so we can consider the soft effective field theory. For example, let's consider the full theory. It's the toy model or single field inflation as you like, and we can split zeta to the hard field with large momentum and soft field with small momentum, and then integrate out the hard modes. So we can do the loop correction for the hard modes and match the results of the loop integrals to be the coefficient in the soft effective field theory. Then this loop collapses to the coefficient of this kind of operators in soft effective theory. Let's look at the part we are interested. So this this zeta A, zeta R operator. But the terms in the soft EFT must also have the dilatation symmetry. So we cannot just have this operator. We need to have a tower of operator which has the dilatation symmetry. Now, so plus and minus branch, zeta transforms like this on the dilatation symmetry, but zeta A is defined as zeta plus minus zeta minus. So zeta A does not transform, and zeta R transforms just like plus and minus. So if we want to maintain the dilatation symmetry, we need to instead of having this operator, we need to have this tower of operator. Okay, so we can expand it, and we also have just one term for zeta A, and this contributes to the one-point green function, which can also be matched from the tadpole diagram in full theory. And we need to add the same term with opposite sign as a counter term to cancel this contribution for the tadpole renormalization. And the counter term must also have dilatation symmetry. So this means when we do the tadpole renormalization for zeta A, we also added a counter term for zeta A, zeta R, and also cancels that part. So in one sentence, tadpole cancellation and the soft two-point cancellation are tied together because of the dilatation symmetry. So now we don't have the operator zeta is star in the soft EFT, which means that we don't have the contribution from the hard loops in the full theory. Okay, now let me conclude. In the context of cosmological perturbation during inflation, small-scale enhancement does not give scale invariant corrections. And we have shown it by explicit calculation at one loop level, and also provided an explanation by dilatation symmetry in soft effective field theory. Okay, thank you.
Thank you. Questions?
Thank you very much for the nice talk. So I'm wondering, like, does dilatation symmetry allow you to make this statement to beyond one loop level?
Yes, I think so, because the statement of soft effective field theory is not restricted to one loop level.
So is there like something like a can one derive something like a word dilatation word identity for the effective action?
Yes, maybe it is possible. Maybe the cancellation of diagram is related to the Walter-Takahashi identity, but we have not studied it yet.
Okay, thank you. Yeah.
Other questions?
So are any of these corrections also important on small scales at all, or just negligible?
Could you say it again?
So
Yeah.
you showed that there's no scale invariant corrections, but
Yes.
as you have this small scale enhancement, do any of these corrections matter or affect that process?
What does you mean? Does that matter for the small scales?
Yeah.
Yes, because this is like we will only calculate for the k goes to 0 limit, but for example, we can have k squared term or k cubic term, then it has some effect at the non-zero part. So in that sense, and we didn't study that part, and we only studied the k goes to 0 limit, so it accounts for the large scale.
Okay, thank you.
Thank you.
Any other questions? Okay, if no, let's thanks Muzi again.
Thank you.
And